Hello YouTube! Today we are going to be talking about how work and energy are related to each other. Um, in particular, I want to quickly just say a couple things about the last one that I forgot to add in. So first off, that because work is the integral of force over displacement, if you have a force on the y-axis and displacement on the x-axis, so displacement versus force graph, you can use the area under that curve to find the work that's done by that force. And that'll come up pretty often on the AP exam. If you see force and displacement, it's going to be energy. And we'll learn later that if you see force and time, it's going to be momentum. So that's the first thing. And the second one is to just highlight a couple little things about the work equation, which is that if the force and work are completely perpendicular to each other, there's no parallel components, so the force does no work. And that's kind of a weird distinction, but when you have the dot product there, it's a lot easier to see why. Versus other classes where we don't get to do the vector math, so anyway. In particular, today we are going to be going over how work and energy are related. If you're good at setting up the mechanical energy equations like you were before, except now you can be like, oh, I can add in the work equation. That's it. You've done it. So in particular, when you do work on something, it needs to gain that much energy or lose that much energy. There is a little bit of a weird thing where like conservative forces only swap energy between different types. So when a conservative force does work, you're not changing your mechanical energy. When a non-conservative force does work, you are changing your mechanical energy. And so for the sake of adding it to your mechanical energy equation, our next step, don't do that for conservative forces. It still does work, but it doesn't do work in such a way that mechanical energy changes. So generally speaking, if a question is asking you about work, you can find the energy, and if, and then that change in energy will be the amount of work that was done, and you can flip that as well. Which means that if you've got situations where you know about forces and you know about distances and you know about two different locations for one object, that last part tends to be really important when we get to momentum, that energy should be a really good tool to use. The work energy theorem can therefore be described as that work is equal to the change in mechanical energy. So if you do positive work, the object can be expected to gain kinetic energy or potential energy. If you do negative work, it can be expected to gain either potential, it can be expected to lose potential or kinetic energy. Yeah. So because of that, what we can do is we can take our mechanical energy at the first location, add it to our work, and that will give us our mechanical energy at our second location. And this is just off of the like, we'll change as final minus initial, add initial to both sides. And I personally like this conception of it because what you can do is you can say, well, I take whatever I started with, I add whatever I gave it or took away from it, minus if it's took away, and that'll equal whatever I wound up with, and that's your equation. And so for me, it makes a lot of like conceptual sense, and that's what I really like about this one. So actually going ahead and doing some examples, I drag a 4 kilogram box, originally going at 10 meters per second with 20 newtons of force at 37 degrees for 5 meters. So a bunch of stuff here, but we got some motion, we've got some forces, and we've got some distances. How fast is it going now if there's a coefficient of kinetic friction of 0.25 between the block and the surface? So you could, in theory, use kinematics for this one. Is it efficient? No. This is a much, much more efficient way of doing it than the kinematics equations, and so that's sort of why we're doing it. So in particular, we've got a situation, let's get our picture down. We've got a box, we are dragging it with 20 newtons of force at a 37 degree angle. It is a 4 kilogram box, which means that mg is 40 newtons, and we are dragging it for a distance of 5 meters. This is our initial, this is our final. And we know that mu k is 0.25. So this is a problem with forces. just as we have been, we should probably start setting up a free body diagram. So we've got mg going down, we've got force 1 at a 37-degree angle, which means we'll have two components. We'll have F1 times the sine of 37 and F1 times the cosine of 37. And we should have some normal force going up and a force of friction going backwards. So, thinking about our different forces, we'll have our x direction, we'll have our y direction. For our y direction, we'll have F1 sine theta from this force going up, positive because it's up, normal force going up, positive because it's up, and gravity going down, negative because it's going down. Because these directions need to all balance out, because the thing is neither accelerating up nor down, that means that our net force will be 0. For the x direction, on the other hand, we'll have F1 cosine theta pulling it in the same direction as motion, so positive, and minus our force of friction going backwards, and I could throw a kinetic in there, and that will be equal to ma. If we wanted to solve this one with kinematics, I'd have to solve out the x equation, get the acceleration, use the acceleration, the distance, and the initial velocity to figure out where it winds up. Nice thing about this is we don't really have to do that. I'm still bringing up these equations because in particular we're going to need to find the force of friction, so we can find the net work done on this thing. But the force of friction is equal to Fn times mu k because it's kinetic friction. And so if we find Fn, which is going to be Fn equals mg minus F1 sine theta, pulling up on it makes there be less normal force, the gravity pulling down on it makes there be more normal force. Then if I just take this and multiply each side by mu k, or plug it in over here, we'll get that our force of kinetic friction is equal to mu k times mg minus F1 sine theta. And so what's nice about this is that I can think about the types of energy that it has to start. It's got kinetic. We do some work to it, and that'll need to equal the kinetic that it has at the end. Since we're asked about the velocity at the end, this is a really nice equation because our only variable here once we plug in for work is our final velocity. And since we know our distances and since we know our forces, it's pretty straightforward to do that. Our two parallel forces acting on this thing are the friction, which is going to create a negative amount of work, and F1 times the cosine of theta, which is the friction is parallel, so I don't have to worry about an angle. F1 cosine theta, once I use the parallel component, will be parallel, or I could just include this cosine theta for the dot product. It will equal 1/2 mv2 squared. If I go ahead and plug in for my earlier force of friction, we'll get mv1 squared plus F1 cosine theta d minus mg mu d minus, and I'm distributing the mu out for reasons that I do not honestly know, mu1 F1 sine theta will equal 1/2 mv2 squared. A little bit of writing, but multiply each side by 2, divide each side by m, multiply each side by 2, divide each side by m, and square root, and we're done. V2 will be equal to the square root of 2 over m times 1/2 mv1 squared plus F1 cosine theta minus mu mg d minus, oops, this should have a d in it, mu F1 sine theta d, where these are our terms for our work. I did mess up a little bit. This should be positive. This should be positive because this negative sign here when I distribute this negative sign here. I probably shouldn't have distributed everything. I should have just written it out in parentheses when I plugged in. That was my bad. Plugging in for our numbers, we'll get the square root of 2 over 4 times 1/2 times 4 times n squared plus 20 times cosine 37, which cosine 37 is a long one. It's a 3, 4, 5 triangle. So it's going to be 12, 16, 20. So this is 16. Minus mu, which was 0.25 or 1/4, times 40 times 5, plus mu, which was 1/4, times, oh, I keep forgetting d, times 5, times sine 37, which is 40 sine 37, or 20 sine 37, is 12 times 5. That's all getting square rooted, so 200 plus 80 minus 50 plus 15, which gives us, oh, times a half. Half of 245 over 2 square rooted. Whatever that is. And your calculator will tell you that. So in particular, highlighting what we did here, we used the forces, but only in so much as we needed to find our individual forces on the object, friction and F1 cosine theta, that were acting parallel to the direction of motion for the object. Once we had that, all we had to do is set up our energy equation and include a term for work with the force times the distance for each of those forces. And once we do that, it's just a normal energy problem where we can pretty quickly rearrange and solve it out. Nothing too weird with the algebra. So these are a little conceptually weird because you have to think about what you would need in order to get the forces, and so there's a few steps in the process, but all the individual steps are pretty simple from a math perspective. You're doing one, maybe two-step algebra, and then substituting it into another equation where you do one, maybe two-step algebra. Continuing the trend out with a problem that's a little more involved because we're going to have some hills, but conceptually is going to be very similar. How would a box that's going 5 meters per second at the top of a hill that's 10 meters high be going at the bottom of the hill if the hill has a coefficient of friction of 0.2 and an angle of 53 degrees with the ground? So again, picture, we've got our block at one location, and then for B, because we're going until it stops, we've got a second location and a third location. During this section of the hill, which has a length, and this section of the hill has a height. There's a couple ways you could think about this one. I'm just going to go ahead and say that my height is 10, which means that this is a 3, 4, 5 triangle. Oh no. I'm going to change the numbers around a little bit just to make them match up a little better. Let's say that this is a 12-meter high hill. Specifically because if we make it a 12-meter high hill, then the numbers should work out a little nicer for the 3, 4, 5 triangle. So our height is 12 here. This is a 53-degree angle, which means that this is the long one, so this is the short one, so this is 9, and this is 15. Great. So, we know that our coefficient of friction for all of this is 0.2. A lot of times on AP problems, by the way, they'll make it so there's no friction on the hill and yes, friction on the ground. For this one, I figured we might as well do both because it's good to spend some time practicing and thinking about both. So honestly, this problem is going to be very similar, except there's also going to be a little bit of potential energy as well. We'll have to set up our coefficient of friction and stuff. while it's on the hill, we'll have mg with mg cosine theta doing work, which we want to ignore because it's a conservative force, so that's already factored into, sine theta, sorry. That's already factored into our mechanical energy equation by including potential energy. So what we can do here is say that Fn minus mg cosine theta is equal to 0 for our y direction, which gives us, with our force of friction equation, that our force of friction is equal to mu mg cosine theta, because those forces are balanced, once again coming up. And so this is nice because this will let us get our work. So if we do our energy between 1 and 2, what we'll get is 1/2 mv1 squared plus mgh equals, plus our work, is equal to 1/2 mv2 squared. And from here, we can just, again, solve for v2. We've got 1/2 mv1 squared plus mgh, our work, and you honestly can skip straight to the second step, is negative force of friction times d, because friction is going to be taking away the energy, mv2 squared. Our force of friction was mg cosine theta times mu. That'll equal 1/2 mv2 squared. Thankfully this time every term's got mass in it, so we can just drop those out of there. Multiply each side by 2, multiply each side by 2, and square root. And once again, we're done. So distributing out the 2, we'll get square root of v1 squared plus 2gh minus 2g mu cosine theta. Times our distance, times our distance, times our distance. I keep forgetting that. I should not keep forgetting that. I think I just get so caught up on how the forces have stuff there that I just I'm like, I did work. I'm done, right? And no, you do have to actually include the distance. So we've got root 5 squared plus 2 times 10 times 10 minus 2 times 10 times 1/5 times cosine 57 is the close one, so 3/5 times distance, which is 15. So it's going to be 2, that's going to be 3. So we're going to have square root of 25 plus 200 minus 4 times 9, which is 28. So root 197 is our velocity for our second location. From there, to get our answer for B, well, all we really have to do is take our coefficient, our friction, when it's not at an angle, which in this case will be just that it's Fn going up, mg going down, force of friction going backwards, so it's actually a little bit easier. These two will balance, which means that our normal force will be mg, which means that our force of friction will just be mu mg. We can take that mu mg, and we're trying to figure out how far it slides before it stops. So that'll mean that if we take our 1/2 mv2 squared that it starts with at the bottom, and we add the work that friction is doing, that'll equal 0, because it needs to have no energy at the end. So we'll have 1/2 mv2 squared minus our force of friction, so mu mg, times our distance, d. That'll need to equal 0. Add mu mgd to both sides. That'll give us 1/2 mv2 squared equals mu mgd divide each side by mu mg. Divide each side by mu mg. And our final answer will be that, no. 4 times 9 is 36. Which means that this is 189. Okay. Sorry about that. Which gives us 1/2 v2 squared over mu equals d. I dropped my g somewhere along the way. So root, oh no, it's not root because it's going to be squared. So 1/2 times 189 divided by 5 times 1/5 times 10. So 2. So 189 over 4, whatever that is, that's your distance. So a couple quick things. If you're doing work until you stop it, the final energy will be 0 unless you're up a hill. In this case, we just had to be careful about including all of our forces and making sure that everything stuck around. Honestly, maybe even easier than the last problem, but I did want to highlight that you don't include the work that gravity does, even though gravity does do work, because that's already included in the potential energy. Potential energy is basically this very special case of that. So that's it. Goodbye, YouTube, and I hope you have a great night. Day. Have fun.